Now we're going to take a quick look at sequences. And in the sequence section, we want to be able to list the terms, talk about a sequence as converging or diverging, write a formula for the nth term, and then use properties of sequences and bounded sequences. This is a bit of a refresher if you haven't seen sequences in a while. So a sequence is defined as a function whose domain is a set of positive integers. So we just have solid integers with them. Although a sequence is a function, it can typically represent using subscript notation, which sometimes throws people for a loop. So we have a sub 1, a sub 2, a sub 3, and that's referring to the term number itself. And then the values that each term is would be 1, 2, 3, 4 in this example. So in here we have terms of the sequence, and then we have what we call a sub n, which would be the nth term of the sequence, which is always going to be an abstract thought, because we never want to list a sequence out to forever. We can't really get there. So a lot of times we use a sub n to stand for that. So if I look at this sequence here, and I want to list the terms, I'm going to simplify each term separated by the comma, and that's going to generate the number sequence that appears to be alternating between the numbers of 2 and 4. In part B, I'm going to do the same thing and simplify by plugging in 1 for the first term number, then 2 for the second term number, 3, and then simplifying them to -1, -2/3, -3/5. This is just an additional example where I can also say that they're recursively defined, meaning that I can get to the next term from the previous one there. So if I think about this sequence, I'm subtracting 5. So instead of saying, well, I would use the sequence, I can say if I just take the previous term and I subtract 5 from it, then I get the next term. So when we're talking about a recursive definition, that's what we mean. It's really just saying, what do I do to get to the next term? And in this case, it would be I subtract 5. Here, if I start talking about the limit of a sequence, that can feel a little weird at first, but sometimes a sequence will approach a number. The previous examples would just keep going up forever. In this situation, though, it's possible, and I'm looking at these numbers, they're getting smaller and smaller. And so if I did continue this out, it would eventually be such a small number we could equate it to 0, or we could approximate it to 0. So if we look at the definition of a limit, it's like taking the limit as n approaches infinity of a sub n. So as I'm looking at what is happening to those terms, then I can define if it converges or diverges. Graphically, we would start to see a sort of asymptotic behavior where there would be a scatter plot for all the sequence values, and then you would kind of see it approach a horizontal asymptote over time. So we could define this in these ways using f of x or a sub n. Basically, it's not anything different from a simple infinite limit. So if you're looking at the terms themselves, you could kind of eyeball them and see if they're decreasing. If you're given the formula for it, like a sub n, then you could actually use the equation rules. Here's an example where I'm given the rule for a sub n. And if I take the limit, and this is probably a little fuzzy for you guys because it might be further back in your memory, but by definition, the limit of that is e. That's the actual definition of the value for e. So it's possible for me to then to say, because I'm getting something out of it, that it does converge, and it's going to converge to e. The limit properties for sequences are very similar to the limit properties of any other equation. I can take the limit term by term. I can do the product of the limit. I can do the quotient of the limit by taking the individual top and the individual bottom. So really those are the general limit rules that we already utilize. A special case within this is we do see a lot of factorial values within limits of sequences and series. So factorials pop up more often than not here. As a special case, just something to keep in mind is that 0 factorial is actually 1. That's something that's a little bit mind-blowing at times, but it is going to be considered 1. So we can apply a squeeze theorem by squeezing the limit between two numbers, just like we did with basic limits in Calculus 1. and that is a complete possibility. So if I did want to use the squeeze theorem, that would be more commonly done with something like a factorial. And so I would just be applying the squeeze theorem. So I know that what I'm given could fall between n factorial and 2 raised to the n. And as I look at those and I compare them, both of those converge to 0. So since both of those converge to 0, and this is in the middle, then I can argue that the final thing is that this actual one, the alternating series, does also converge. So it's just a little bit of a play on the squeeze theorem. This probably, if you were looking for more examples of this, sine x over x and the limit of that is a great example to look up for squeeze theorem help. So this would just be finishing out showing what happens there as we're able to do the actual squeeze limit. So we can say now that if we have a negative number, it doesn't affect things as long as the limit of the absolute value goes to 0. So what this does is this makes the -1 that's present here, that makes that almost negligible. I don't have to really account for that -1. So I'm looking at the absolute value, making that a bit easier.